In this series of video, we're going to see two comparison tests. One of them is called the comparison test. Let's see what that one's about. We're starting out with the assumption that we have two series, sigma a sub n and sigma b sub n, and they have positive terms. It's really important to note that the comparison test is going to apply to series with positive terms. We are going to make two statements here. One, if sigma b sub n is convergent, and a sub n is less than or equal to b sub n for all n, then sigma a sub n is also convergent. In other words, if the infinite series denoted by b sub n adds up to a finite number and all the a sub n's are smaller than b sub n, then a sub n is going to add up to a finite number as well. This is kind of like the integral comparison test you would have seen in the previous chapter. The second part to this supposes that sigma b sub n is divergent and that b sub n is less than or equal to a sub n for all n. If that's the case, you probably know what's coming, right? Then sigma a sub n is also divergent. With again the idea being that if I add up all the b's and I get an infinite result and all the a's are bigger than the b's, then of course a is going to give me an infinite result as well. So again, to repeat, part one says smaller than convergent is convergent. Part two says larger than divergent is divergent. People sometimes draw a wrong conclusion though. Larger than convergent tells me absolutely nothing. It could converge or not. Likewise, smaller than divergent tells me absolutely nothing. So we have to make sure we have the correct inequality for a comparison series. And the idea here is I want to know about a series a sub n. I'm going to pull a series that I already know about, b sub n, and use that to draw a conclusion about a sub n. Well, let's look at the proof of the comparison test. Part one is about convergence. That's where we're going to start. Let s sub n equal the sum as I goes from 1 to n of a sub I. We're going to let t sub n be the sum as I goes from 1 to n of b sub I. And then we're going to let t be the infinite sum as n goes from 1 to infinity of b sub n. If a sub n and b sub n are positive, as stated in the statement of the test, then the sequence of partial sums s sub n and the sequence of partial sums t sub n are increasing. And t sub n, the partial sums, approach t, the infinite sum, so we know that t sub n is less than or equal to t for all n. Further, by assumption, a sub I is less than or equal to b sub I, which means that s sub n, the partial sum for a, is less than or equal to t sub n, the partial sum for b, which means that s sub n is also less than or equal to t for all n, t being the infinite sum. So the sequence s sub n is bounded above. Now it may have gone just kind of past some people, but here we've got, for s sub n, we've got a sequence that's increasing and bounded above. It follows that the sequence s sub n converges by the monotonic sequence theorem. That means that the series sigma a sub n converges. Here we started with a statement that sigma b sub n as n goes from 1 to infinity was equal to t, which implied that it converges, and then we ended with a statement that sigma a sub n converges, and that's what we needed. Part two of this was a statement about divergence, and we're going to go to that one now. It goes quicker. If sigma b sub n is divergent, then t sub n approaches infinity. But a sub I is greater than or equal to b sub I, which means that s sub n is greater than or equal to t sub n, which means that s sub n approaches infinity as well, which means that sigma a sub n diverges. And now that we have that established, we'll make a note here. The comparison test is often used with a p-series or a geometric series. See, those are two series that we know something about. Let's see how this works. For the series sigma n going from 2 to infinity of 1 over the square root of n minus 1, we're going to determine whether the series converges or diverges. I'm focusing now on where all the n's are, and I see I have a 1 in the numerator and a square root of n in the denominator. There's a minus 1 there, but as n goes to infinity, that minus 1 is going to be much less important than it looks right now. The comparison test, it requires us to compare to a series. In order to determine to what series I want to compare this, again, I'm looking at the n, and it's in a square root, and so I'm going to compare this to 1 over the square root of n. Now here's something people blow right past a lot. Take the moment to look at the denominators and see which series has bigger terms. The one on the left, 1 over the square root of n minus 1, has a smaller denominator and therefore a larger overall result than 1 over the square root of n. So I have that 1 over the square root of n minus 1 is larger than 1 over the square root of n. We also know that sigma n going from 1 to infinity of 1 over the square root of n diverges. It's not enough just to say that. You got to say why. Think about this like you're a lawyer in a court of law, and you have to be able to defend absolutely everything you've said. I have said that this diverges. How do I know that? How do you know this? It's a p-series with p less than or equal to 1. We've already established something about p-series. So folks, now I have a series whose terms are larger than a series that is known to diverge. So the sum as n goes from 2 to infinity of 1 over the square root of n minus 1 diverges by the comparison test. Now as an aside, suppose our series had started out as 1 over the square root of n plus 1, and I wanted to compare that to 1 over the square root of n. Now what I have is a larger denominator. The square root of n plus 1 is larger than the square root of n, and so I have a smaller overall result. Therefore, I have a series that is less than a series that's known to diverge. This is the wrong relationship. I cannot use the comparison test for the 1 over square root of n plus 1. I have to use a different test, and we'll see that in another video.